This module is about inferential statistics, and we're going to start with a conceptual review of what inferential statistics are and why they are useful. Just as a brief review of descriptive statistics provide a summary or a snapshot of our data. It can include measures of centrality, which would be something like the mean or the median, and then measures of dispersion or spread, which is the standard deviation or variance. Inferential statistics, on the other hand, help us draw conclusions or make decisions based on our data. So there are two common classes of inferential statistics, and these are based on association and based on differences. So association-based inferential statistics would be something like correlation, and some examples would be IQ scores between parents and children. We know that IQ scores tend to be correlated between parents and children in that parents who have higher IQs tend to have children who have higher IQs. Another example would be comorbidities between depression and anxiety. People who are diagnosed with depression are also more likely to be diagnosed with anxiety. And finally, age and social media use would be another example. Younger people tend to use more social media. So examples of group difference-based inferential statistics would be something like the heights of men and women. So men tend to be taller than women. This is a difference between two groups. Another example would be the outcomes for participants in a treatment trial for a drug. So in these examples, you often have a group that takes a placebo and then other groups that take some kind of experimental drug, and you hope to see that the experimental conditions have better outcomes than the placebo condition. And finally, if you compare income for college grads versus non-college grads, you also expect to find a difference. You expect college grads to have higher average income than non-college grads. So this brings us to the sort of problem that we're faced with, which is that we want to make inferences about populations, but all we can really know about are samples. And just as a quick review of the definitions of these terms, a population represents all possible units of measurement. So this would be something like the difference in heights between all men and all women, whereas a sample is just a subset of the population. So we can measure a sample, we can measure 100 men and 100 women, and we want to try to use that to make inferences that can be applied to all men and all women. So a thought experiment that can help us sort of understand what's going on with this involves taking a God's eye view. So let's say that I'm a science fiction author, and I'm writing a book with two alien species, Klingons and Smolkans. Klingons tend to be slightly taller than Smolkans, and I know this because I invented them. In fact, I know that there are exactly 1 million of each, and I know that the average height of all 1 million Klingons is 72 inches, and the average height of all 1 million Smolkans is 70 inches. We can actually visualize this with a graph. This is what's known as a density plot. We don't need to know too much about the technicality of what this plot is doing. All we really need to know is that where each curve is taller, that means there's more of each species that are around that height. So here we see the blue line, which represents Smolkans, peaks at 70 inches, and this is the mean height of all Smolkans. And then we see the red line peaks at 72 inches, and this is the mean height of all Klingons. And then we have these dashed lines, which again represent these means, and they cross right around the peaks of these curves. So as the author, I know this. I know that there are 1 million of each, and I know that their mean heights, and I know the distribution of their heights, because I'm the author. Now, in my story, there are actually 5 starship captains, and they are doing research on alien species. And they want to try to determine whether Klingons are taller or Smolkans are taller. So each one observes 25 Klingons and 25 Smolkans, and then compares the mean height of each species of alien. So our first captain, Captain Dirk, creates a density plot like the one we looked at before, but this time he's only looking at 25 of each. So these plots aren't nearly as pretty, they're much more jagged, they're not as symmetrical looking. But what we do see here is that on average in his sample, Klingons tend to be a bit taller than Smolkans. Captain Ricard also obtains a similar result. He doesn't get the exact same mean heights or the same distributions as Captain Ricard, but he also sees that in his sample, Klingons tend to be a bit taller. Captain Mainway sees a similar result, but Captain Blisco actually finds they're almost exactly the same heights in his sample. There's very little difference in the mean heights between Klingons and Smolkans in his samples of 25 of each. And then Captain Marcher actually finds that Smolkans are taller. Even though he took another sample of 25, in his sample, we see something that is not representative of the population, in the sense that Smolkans are taller than Klingons. This is an example of a sampling distribution. So we've looked at 5 different samples, and we got 5 different mean heights for both Smolkins and Flingons. And this is because samples tend to vary around the populations. And we could actually think of each mean from each sample as being drawn from a population of means, making these samples of 5 means actual observations from a population. This is a sample of each set of Flingon heights and each set of Smolkin heights is a sample of means. This population of means is known as the sampling distribution, and it can be thought of as a meta distribution. So it's a distribution of distributions. And what we have here, again, is a sample of 5 means from this sampling distribution. And here we see visually a comparison between the population distribution and the sampling distribution. So the population distribution is the heights of all 1 million individual aliens of both species. The sampling distribution is the mean of 1,000 different samples of 25. So each of these observations on the right represents the mean of a sample of 25, and this is done 1,000 times, and this allows us to get a look at what the sampling distribution would look like. And we see here that the means of the sampling distribution match the means of the population distribution. So how does this help the captains make inferences? And if you want, you can pause the video here and maybe think about this a little bit. This may be a good sort of discussion topic, and it may be something where you want to try to come up with an idea based on what you know about statistics for how the captains can now make inferences about Flingons and Smolkins based on their sample and based on what they know about sampling distributions. Remember, they don't know the population distribution. So this might be a good place to pause. And now I will continue to explain. So how does this help the captains? Captain Picard, or Rickard, sorry, we don't know who Captain Picard is. Captain Rickard has an idea. First, hypothetically, assume that Klingons and Smolkins are the same. This is called the null hypothesis. Next, determine how unlikely it would be that our observed sample came from this null distribution. This is the underlying logic of t-tests, of f-tests, of ANOVA, of most of our statistical tests that we do. Now, there are some cautions that you need to be very sensitive to and aware of when doing this type of inference. These tests don't actually prove anything. They're not the probability that the difference observed in our samples is somehow, quote, real. What it is the probability that the observed sample that we obtained, or one more extreme, would be drawn from a distribution that didn't really have a difference. So if this probability is very small, it would indicate that our samples don't come from this null distribution. It would indicate that they come from some alternative distribution where there is really a difference. Now, this is just one way to think about statistical inference, and it's historically one of the more common ways. It's definitely not the only way. There are a lot of people who argue it's not the best way, and some people even argue it's not a very good way. And the truth is there's lots of exciting innovations and debates happening in applied statistics. I think a lot of people tend to think of math as something that's relatively solved in the sense that, like, we know a lot about mathematical laws and properties. But the truth is in statistics, this is a very active, growing field. And the field of statistics, as we conceptualize it in the modern day, isn't actually that old. And a lot of the work that we're doing is based on ideas that people have had within the last 100 or even 50 or even 10 or 25 years. And of course, just as a reminder, don't forget to report effect sizes in addition to these inferential statistics, and we'll talk about a little bit more about those in subsequent videos.